Hello, everyone. Welcome to another episode of Science and Technology Q&A for kids and others. So we seem to have a whole bunch of questions here that have come into our form or been asked in previous weeks and not answered. Let's see. Maybe we should jump into a difficult one here from Anoni Mouse, I guess. The question is, so do we live in a simulation or not? You know, I have to say, this is a question which people have been asking in different forms for many, many centuries. The question is, we experience things internally. We experience the fact that I'm looking at a camera, I can touch, my computer, I can do all these kinds of things. There seems to be a real world out there. But how do we know there's a real world out there? Why isn't it the case that maybe we're just, our mind is just in a computer somewhere, and everything we're experiencing is just aspects of what's being fed into the program that is running to make our mind, so to speak? How do we know that there's an external reality that is beyond what is just that is not just being sort of fed to us in some virtual way? And I think one of the popular thought ideas of recent times is, well, the way that our technology is developing, we are making, great video games. We're talking about metaverses. We're talking about hanging out all the time in this kind of virtual world. And we're talking about maybe having direct connections between the virtual world and our brain and so on. How come? And that will be the future of our own civilization and our own technology development. Well, if that's the future, maybe we're living in that future, and that future is simulating the past, as in the kinds of things that we experience today. Maybe, in fact, really, in some sense, it's 3000 AD or something, and we're all just in some virtual environment which is simulating 2022. So the question is, can we sort of unpack that idea? Does that idea make any sense? How do we think through that idea? And okay, so I sort of have a somewhat perhaps fresh thinking about this, because we now think that we understand how to make a fundamental theory of physics. In the past, one had always thought, well, there's the physical reality of the world and physical laws and gravity operating on things and things dropping and, actual atoms and all this kind of thing. And then that's the physical world. And if we were sort of in a video game, we might have a software emulation of a world, but it's different from the physical world. And part of the point there is, well, we don't know how the physical world works. But what's happened as a result of our physics project in the last couple of years is we have a pretty good idea how the physical world works, kind of all the way down. And what we realize is that the physical world is, we think, made, and I'm not going to go through the whole story here, but in the end, for example, space is made up of these discrete atoms of space and this giant network that represents how those atoms of space are related. And all the things that we experience in the world are the result, or we can think of them as being the result of essentially running a program operating on this giant network connecting the atoms of space and so on. So in a sense then, when I say everything we experience can be thought of as being the result of this sort of abstract rule running on this giant network that represents atoms of space, the can be thought of is an interesting term. Okay, so let's imagine that we say, I don't know, the Earth is going around its orbit, going in its orbit around the sun, and it is following, it's pulled into the sun by the inverse square law of gravity and so on. And we might ask the question, is the Earth really moving according to the inverse square law? Or is that merely a representation of how the Earth is moving? And the Earth is moving in some way that we're not describing, that's some sort of intrinsic physical way that it's moving, but it is merely described by this mathematical construct of the inverse square law. Well, in the way one starts thinking about these things, at the first level, what one has is merely a description of how to think about how the world works. So we say we can represent how the world works in terms of these abstract atoms of space and rewritings of these networks corresponding to abstract atoms of space and so on. But we're not committing ourselves to that sort of actually how it works, that that's actualized. We're saying that that's a representation of how it works, but we're not saying that's sort of intrinsically how it actually works. Now, in other words, I think a term that's been used by philosophers, it's something like, how do you put the fire into the model, so to speak? How do you go from a mere description to something which is actually the way it works, so to speak? Okay, so this gets kind of tricky, but and I think we have to go a couple of different levels to understand how this works. The thing that is, first thing to say is, if we think we have a description of how the whole universe works, these atoms of space, these rules, the reconfiguring them, et cetera, et cetera, et cetera. One thing that's a little weird about that model is that we ourselves are part of that model. In other words, whatever is going on in our brains and that is producing our minds and so on, it too is represented by atoms of space and rewrites of atoms of space and so on. And so we're in this slightly odd situation where the observer of what's going on is actually embedded within the system itself. And that puts us in a slightly different situation from the more common situation where we're saying, there is this thing out in the world, we're making a model of, I don't know, the flow of a fluid or a planet moving in orbit, and we are looking at it from the outside. We are observing it from the outside, and we're saying, well, we can explain what's going on by this or that rule, but we are thinking through how those rules work outside of the system itself. The situation with the whole universe is quite different because we are part of it. So we are kind of experiencing it from the inside. So that's the first thing to realize, is that our sort of observation of the world is from inside the system. Now, I want to comment on, we really want to talk about, is the universe a simulation, so to speak? And by which I mean, what does one mean by, is the universe a simulation? What I think one tends to think one means is, well, there's us on the inside experiencing what we think we're experiencing in the universe, but there's an outside. There's the video game player on the outside, the kind of sort of the super being that's playing the video game, and we're merely creatures in the video game, so to speak. So what does it mean that there's sort of a creature on the outside? It means, well, the first question is, does the creature on the outside just set the game in motion and then it just runs itself? Or is the creature on the outside every so often pressing a key and saying, I want this person to do this or that? It's funny because this is a deeply sort of theological kind of question. And it's kind of like, this is all the question of miracles, so to speak. Let's say the world runs according to certain natural laws, but every so often, in ancient Greek times or something, it would be the Olympians would throw a thunderbolt at the appropriate place and would sort of change what's going on. Even though there's sort of an ordinary way the world operates, there's a certain density of, from the outside, either the creature playing the video game or the Olympian on Mount Olympus is throwing the thunderbolt and changing what happens in the world in a way that goes outside of the natural laws of the world. So one has to first ask the question, is that what's going on? Are there lots of miracles? Or is it the case that what one's mostly dealing with is just the player started the video game, they pressed go, and then the universe is after that just running according to the rules defined for the universe? Well, let's assume that we, insofar as we believe there are natural laws and we believe that there is not a high density of kind of, quotes, miracles, thunderbolts that come from nowhere type thing, then we're really in a situation where in a sense, at very best, the simulator, the creature on the outside doing the simulation, is at most just saying, I'm selecting this game. Okay, this is the, Earth 2022 game or something, and, humans, whatever, and then I press go. And then that's it. And then everything else is just running according to the natural laws of the universe that we gradually managed to uncover using science. So, okay, so in that scenario, the thing that we're saying is there's sort of a thing on the outside, and one feature of the thing on the outside is there's a choice about what universe. Do they run the Earth 2022 game, or do they run the Torsetti 3074 game, or do they run something else? Or do they run a game with a universe which is 8.5 dimensional? In other words, is there a choice in the creation of the world, so to speak, on the part of the gamer on the outside? So that's one question, is what one imagines if there is a simulator. One imagines a couple of things based on our sort of everyday experience of sort of the computational process. One thing is there's a choice in what program to run. That's one feature. The other feature is there's a substrate on which the program is running. So in other words, we're saying that, yes, there is this way of describing how the world works in terms of atoms of space and this and that and the other, but if it is a simulation, it is running on something. There is a computer. There is the Uber computer, so to speak, which is being run by the Uber creature that is the thing on which our universe is operating as a program. So there's this idea that there is some substrate, there is something there's a chooser of the program, and then there is a thing that the program is running on. Okay, well, so now the question is that, so that's a possible sort of model of what's going on. Okay, here's why I think that model doesn't make any sense. And this requires us going even deeper into some kind of rabbit hole to understand this. So what I said is there's this kind of, we think we understand what the universe is like kind of all the way down. We know what the atoms of space are like. We know these rules that update the atoms of space, all that kind of thing. Now, in principle, all that stuff could be being emulated on a computer, or it could just, or the atoms of space could be what sort of really exists. But okay, we're going deep into a rabbit hole here, but let me keep going for a moment. So one of the big questions about sort of finding a fundamental theory of physics is this. Let's say we have the rule that says how the atoms of space are updated, and that's the rule that if you just keep running it for a long enough time, you'll just get the whole universe. That would be a remarkable thing to have. One can hold in one's hand this rule, and maybe it's one line of Wolfram language code or something, and one says, just run this rule for a huge amount of time, and you will get precisely this whole universe of ours. So then the thing that would next come out is the question, well, how come we got this particular universe? How come we got universe number 2711 or something, and we didn't get universe number 30,214,000? Who got that universe? Why did we get this universe? And particularly if it's a simple universe to where the rule is simple, even though the universe itself may be very complicated, you might start from this very simple rule. How come we got this particular simple rule? It kind of seems wrong. Just like you say, well, where do we live? Do we live at the center of the universe? People used to think that. We now know that we live in a pretty random place on the outer part of a pretty random galaxy out of the 100 billion galaxies in the universe. There's nothing very special about where we are in physical space, so it seems, other than that for us it's special because we're here. Okay, so in the space of all possible rules, it also seems implausible if somebody tells you, well, we actually live in this very special universe that was a very, specified by this very simple rule, and all those other universes that might be have these much more complicated rules, and we're very special here. That just seems, it doesn't seem like a plausible claim. It seems very kind of haughty to think that we would be in that very special universe. I worried about this for ages, and I realized the following thing. what if we're talking about these rules for the universe and how things run? Now, one thing I didn't kind of mention is that you specify rules for how this network that is the connections between the atoms of space, you specify these rules that say whenever there's a little piece of network that looks like this, you should rewrite it into one that looks like that. You could rearrange it, you sort of thread things in this kind of abstract representation of all these connections. It's kind of like the friend network of the atoms of space. You're reconfiguring the friend network of the atoms of space according to some particular rule. And you're doing that whenever you see a little piece of friend network that looks like this, rewrite it to be one that looks like that. And you do that whenever you see it. Now, the thing that happens when you do that is that there might be many different ways in which you can do that updating, and they might even overlap. They might even be, do this one first, then this one, and so on and so on and so on. There are lots of different possibilities. One of the great things with our model of physics is the existence of those many possibilities leads to many threads of time, which precisely gives one quantum mechanics. And it gives one the mathematical formulation of quantum mechanics and so on. It seems to be how quantum mechanics really works. Now, one of the weird things about that is there are these many different possible histories for the universe, and we're saying that in some sense, all of those histories are realized. But again, one of the bizarre things is that we are embedded in this universe that has many histories, and where there are branching histories and merging histories and so on. So in a sense, and this is sort of the story of quantum mechanics in our models, is that our minds, our brains, are also subject to this merging of different branching and merging of different threads of history. So it's kind of like, how does this branching brain perceive a branching universe? Or the weird things of quantum mechanics are associated with that kind of question. But okay, so we've got this idea that you've got this rule, and maybe it's a simple rule, and you just apply it wherever you can, and that leads to this complicated history for the universe, many threads of history. We kind of conflate those together as kind of observers who think there are definite things happening, and so on and so on and so on. Okay, so then you start thinking, well, what if instead of running a particular rule in all possible places, you run all possible rules in all possible places? So there's no special status that you give to rule 1374 or whatever it is. You're just saying run all possible rules in all possible places. Okay, that seems like an unbelievably complicated, messy thing to have. And it seems like, how could you say anything based on running all possible rules in all possible places, in all possible ways for as long as you want? Well, it turns out that what you get is not just a total sort of anything can happen kind of mess. And the reason is essentially, so what you're effectively doing, you can think of that as, imagine that you have all possible programs for computers, and you're starting them off with all possible initial states, and you're running all these possible programs, and you're doing it for an infinite time. What you'll end up with is this big entangled mess of different things that happen. But a very critical fact is that two different programs might end up producing the same output. And that very fact of the fact that two different programs that seem like they're on different threads might actually merge in what they do at a certain moment. And then those different programs might diverge again. But the point is that it's not the case that all these programs are just completely independent in what they're doing, because different programs can end up producing the same results. And so if you are sort of an observer of that universe, and even more so if you're embedded within the universe, as far as you are concerned, these two programs, they just made the same thing, and you can't tell, if you're just in that state, you can't tell which program it was that was responsible for it. Okay, well, in this kind of rabbit hole here, the next thing to realize is that we are, just as we are embedded, if we believe that the universe is running sort of all possible rules, we are embedded in this thing in which all possible rules are being run. And so we are then sort of, our experience of the universe is based on also operating, sort of having these many different threads of history that correspond to all these different possible rules for the universe. But there's an important feature about us and the way we think about things, which is that we think definite things happen. And that's, even though there are many possible threads of history, we think definite things happen. There are many special features of us. For example, we think we're persistent in time. We think that it's the same me at this moment in time and 1 second later. It's kind of weird that we think it's the same me, because if we went down and we looked at how are we made out of atoms of space, we would be made of different atoms of space. At a quite different level, you could say that, through the course of our lives, the various different atoms that make up the cells in our bodies gradually get turned over, yet we don't have any trouble saying it's still the same me when I'm 5 years older. It's this idea that there's an essence of us that is kind of persistent through time, even though in that particular case, the material stuff of which we're made changes. And it's in a more extreme case, so an analogy one can give, imagine you've got some water and you've got some vortex that's moving through the water, or you've got some tornado that's moving through the air. Even though the tornado involves different molecules of air as it moves, it's still identifiably the same tornado. I just wrote a piece that I think will get posted today called On the Concept of Motion, which is one of these pieces that you would think somebody would have written 2,000 years ago. And people did write about these things 2,000 years ago. But this question of how you can have a thing that can move and maintain its identity is actually a non-trivial question in terms of these kind of models of physics that involve sort of atoms of space and things like this. It's not obvious that you can have a thing that is like a tornado or something, or that in which the sort of the underlying stuff in it changes, but the thing itself is preserved. And how that works for things like electrons and so on in our models of physics is a non-trivial question. But okay, back to sort of our experience of the universe. So in the end, what's happening is in this kind of, I call it the ruliad, this thing that is this sort of entangled collection of all possible computations. We are kind of observers of that. We are experiencing kind of the universe from some particular vantage point in that ruliad. That is, the state of our mind or something corresponds to some particular piece, some particular place in that giant ruliad of all possible computations and so on. So in a sense, we can think of it as we are at a particular place in rulial space, just like we're at a particular place in physical space, and we experience the universe from this planet going around this star in this galaxy, et cetera, et cetera, et cetera. That's where we experience the universe from. So similarly, we're at a particular place in rulial space. We are experiencing the universe with a particular set of kind of interpretations of what is going on in the universe. We attribute particular rules to what's happening, and those correspond to the way that we, with our minds, are parsing what happens. Let me try and make this a little bit more concrete. So, a good analogy is, I don't know, something like a fluid like water. We interpret that as a thing you can pour. You pour it and this stream of fluid comes out. Underneath, there are a bunch of molecules in there, and they're all bouncing around in complicated ways. If we were, for example, creatures that were vastly smaller than we are in the size of molecules and so on, this whole, you pour the liquid and it comes out in a stream and so on, that's not what we would say. We would be talking about individual molecules and how they bounce around and things like that. So in a sense, there's a question of how we parse the world around us. We parse something like the fluid in terms of something that's flowing, and we can pour it and things like that. But that's a feature of our way of our scale in the universe, the kinds of things we pay attention to in that system. And so it is ultimately with the whole universe that there are an infinite number of ways that we could parse the goings on inside this ruliad. But we are, in effect, we exist at a certain place in rulial space, and that is causing us to have this particular way to parse this whole ruliad of possibilities. Okay, why is this relevant to the whole simulation question? Here's why. The ruliad is all possible computations with all possible initial conditions, run for infinite time, and so on. The thing is, there is only one ruliad. there is no choice about the ruliad. The ruliad is, in a sense, all possible computations. So we could have different ways to represent them in terms of one model, Turing machines, this kind of machine, that kind of machine, all these different ways to represent computations. But in the end, what we've got in the ruliad is this thing that is a purely formal object that is that there's only one of. It contains all the different possible axioms for mathematics. It contains all these different things, but there's only one of it. We can describe it in all sorts of different ways. We can say, well, we're describing it in terms of, the operation of Turing machines or the operation of some other kind of computational system, whatever. But in the end, the formal object, there's only one of it. There's no choice about how it works. So that means that there is, in a sense, there's nothing to discuss in terms of, did the simulator, did the outer creature that's playing the video game, did they put in this cartridge? I don't know if video games even have cartridges anymore, but did they put in sort of this game or that game? Well, there's no choice of games. The only game is the ruliad. And the ruliad is a representation of kind of what is, the ruliad is a necessary formal kind of thing. Just like if I define what 2 is, and I define what plus is, define what equals is, and I define what 4 is, 2 plus 2 equals 4 is not something where there's a lot of wiggle room, where I say, well, it might be true or it might not be true. Given the definition of terms, 2 plus 2 equals 4 is always a thing. And the same is true with this ruliad. It's a necessary formal object, and there's only one of it. So then so there are really 2 things about the simulation. One thing is that, is there a choice in the simulation? Is the simulator the kind of sort of the theological figure, so to speak, that's choosing the universe? Is there choice? And what we're saying here is, when it comes to the ruliad, there is no choice. The ruliad is the representation of all formal things, and there's only one of it. Okay, so that's the first thing. There's no choice. The second thing is, what's the substrate on which this is running? Well, it doesn't have a substrate, because it is merely a formal thing. It doesn't have there's no reason to talk about a substrate, because it is merely formal. When you say 2 plus 2 equals 4, you could say, well, what is that running in? It's not running in anything. You could say, I could implement it with stones or something, but that's just a taking of that formal thing and turning it into something that I'm representing in terms of stones. But there's a formal thing that we don't have to say where it's running at all. And the ruliad is such a formal thing. But the point is that we are embedded within that formal thing, and our experience is being derived from the operation of that formal thing. And there's no need to sort of appeal to some actualization substrate, because everything that goes on, going all the way from sort of what's the intrinsic thing of the universe to what is the thread of experience that we have in the universe, all of that can exist within this kind of purely formal system. So we don't have to kind of go outside that. So in a sense, there's no longer a reason to have a substrate there. There's no substrate that needs to exist. There is this formal thing which necessarily exists and from which we derive our experiences. Okay, so then the question is, well, so does that mean the simulation argument is just completely dead? Well, at some level it is. But one question is there a choice about the universe? Is there something that is, we said, well, there's no choice about the ruliad, and there's no sense in which there is an outer creature determining our universe. But the question is there still choice? And for example, that's a question, do we still have agency in determining what our world is like, and so on? Or is it just, there's this clockwork thing and it's just running, and there is no, there's no sort of free will, everything is predetermined, et cetera, et cetera, et cetera. Well, at some level, the ruliad is predetermined. It's just a thing that exists. But the question of where we are in the ruliad and how we choose to parse it, that in some sense is much more a matter of a sort of, in some sense, arbitrary choice. In a sense, our experience, so how do we experience the ruliad? How do we experience the universe? we experience the universe through, for example, our senses. We are seeing things, we're hearing things. They're things that are, we exist on a certain scale. We are not seeing individual molecules in the air. We are seeing things about, the flow of some water or something like this. And the question is, and so in a sense, our biology and our biological history, the history of evolution and so on, is determining how we experience the universe. It's determining how we parse the universe. In some sense, it's determining our position in rulial space. And so can we move our position in rulial space? Well, yes, we can. Imagine that we had completely different senses. Imagine that in some future technology, we're able to understand things that happen at the level of atoms of space, and we're able to do all these different things. Then our experience of the universe will be different. And the rules which will describe the natural laws which we'll use to describe the universe will be different. And so in some sense, we have changed our universe at that point. So in some bizarre sense, rather than it being the case that from the outside, there is there could be a controller of the universe that's setting the universe the way it is, rather there's just this ruliad that's this sort of all possibilities, but we inside this are making the choice about how we choose to explore and parse and understand what's there. So in some sense, we're the ones in control of sort of what our universe is like, because we're describing our universe right now in terms of, I don't know, continuous space and stars and black holes and things like this. We could be describing our universe in terms of, oh, there's this particular little quantum particle here, and there's this weird thing here that's this connection between these two pieces, and so on. We could be describing it in a completely different way. And in some sense, that would give us a different experience of the universe. So in some bizarre sense, rather than it being a conceivable thing that there is a sort of outer simulator of the universe, rather the universe is sort of a necessary thing, but the features of what the universe is like, the sort of the choice of game in a sense, is kind of all on us. And it's all on us having chosen to parse the universe in the way we do, which is based on sort of our sensory experience, and it's based on kind of even our ideas about science, like the things that we might say, oh, did you notice this or that feature of the universe? Well, we notice it because we learned some science or something, and without that science, we never would have noticed that feature of the universe. And so we would, in a sense, be parsing the universe in a different way. So, okay, so that's the, gosh, that was a bit of a long, just to talk about, this whole question about sort of, are we merely, our sensory experiences merely being fed to us sort of by a conscious, by some purposeful outside thing? In a movie like Matrix, that was kind of more or less the idea. I don't know, I think it sort of segued into things that were closer to science of mine, about, I didn't quite understand some aspects of what happened in the movie. So in the later parts of the series. So I can't speak with authority about what was intended there. But I think again, sort of trying to summarize this, since we now think we know what physics is like all the way down, we can kind of say, is there room for a simulator there? And the answer is, when we drop all the way down to this ruliad, there just isn't the room for a simulator, because everything that we drop down to is necessary. There is nothing there that is a choice. And so that's part of the story. And then this question of, then this surprise kind of sting in the tail of, well, does that just mean we're stuck with the universe as it is and there's no choice in everything? No, actually, it isn't true, because there is sort of our choice in how we choose to experience the universe. It is the laws of the universe, ultimately at the level of the ruliad, are completely determined. But there are many things that are going on there, but we are choosing to pay attention to only particular things, and those represent the universe as we experience it. as opposed to the universe as some alien might experience it, that would have a different, sensory experience, different science, et cetera, et cetera, et cetera. Let's see. That's very weird. Okay, let's see. Okay, William is asking, boy, you guys are asking me to do serious philosophy in a very, I mean, let me be clear that these questions about sort of external experience and so on, these are long-running, deep philosophical questions, which we have a different perspective on now, primarily as a result of the physics project. And I would have answered differently a couple of years ago. I didn't know any of these things about the ruliad and so on at that time. That's really new set of ideas. So William is asking about why do we perceive that we can make choices? What does it mean to make a choice? So this is, again, a long-running philosophical question about free will versus determinism. The question is, do we have a free will? Is our will free of, can we make arbitrary choices, or is everything predetermined in sort of the behavior of the world and of us? So here's a way to think about this a little bit. So one of the things that can happen is, let's say there's a rule, there's some very precise rule that determines every aspect of how we will operate or how some system will operate. What one might have thought is, if there is a rule that determines how everything works, then it must be easy to predict what the thing, the person, whatever will do. And if you go back to, science fiction movies of the 1950s, 1960s, they had robots in them. And one feature of the robots is they operate, quotes, according to logic. And it becomes, they do very sort of easy to predict things. Oh, it's operating according to logic, so it will do this and this and this. The general belief was that if there were definite rules, let's say simple logical rules or just logical rules at all, that determine the behavior of the robot, it will be readily predictable what the robot will do. Well, that turns out not to be correct. And that's something that came out of particularly work I did in the 1980s. This idea that even though you might know the rules by which a system operates, when you actually run those rules, you can get, in a sense, irreducibly complex behavior. You can start things off, you have a little thing with one black cell in some array, and you run it for a while, and you get this really complicated pattern. The pattern is completely determined by the rules. Every time you run it, you get the same pattern. The rules absolutely determine what's going on. It's kind of like in sort of math, you have the digits of pi. They're completely determined by saying they're the ratio of the circumference to the diameter of the circle. When you generate them 3.14159, et cetera, that sequence of digits in many respects seems completely random, yet it comes from a completely deterministic, definite rule. Well, so it is possible to have a situation in which when you run the rule, it does these very complicated things. And the only way you can find out what's going to happen is essentially just to run the rule. You might say, gosh, I think I should be much smarter than this little tiny, program, the very simple program and so on. I, as a human with a brain and a mathematics and, sophisticated computers and so on, I should always be able to jump ahead. And even though it took 1 billion steps for this program to figure out what it did after 1 billion steps, it's just wasting its time. I should be able to just do something where I can jump ahead and in 100 steps tell you what you're going to do after 1 billion steps. Turns out it doesn't work that way. Turns out there's this phenomenon I call computational irreducibility that means you can't expect to jump ahead. Now, that phenomenon has sort of it's a bad feature in some sense for science, because it means you can know the scientific rules by which something operates, but not be able to predict what the thing will do. Something that's important if you're trying to sort of figure out, I don't know, some epidemiological thing or something, and you say, I know the rules, I can figure out what it's going to do. Well, not necessarily. You might have to run the rules through every step, basically, to find out what will happen. So that's sort of the bad news about computational irreducibility. The good news is, if you're the critter that is running according to these rules, then you're sort of not wasting your time. If we're running our lives according to these rules, one might say, if one could sort of jump ahead, don't lead your life. The answer is just going to be 42. And there's nothing is achieved by actually leading your life and going through all those different steps of this computation. But computational irreducibility tells you there's sort of an irreducible thing that's achieved by doing that computation. You can't know the outcome except by doing the computation. And this relates very much to the question of free will, because what it's basically saying is those robots from the 1950s that obviously didn't have free will, they, you could poke them in this way and that way, and simple logic would tell you that they will do this. They obviously don't have free will. But if they have computational irreducibility, you poke them and they have this experience and that experience, and you can't tell what they're going to do any more quickly, effectively, than their brains can go through and figure out what they're doing. So there's no sense in which sort of you can go from the outside and say, look, that thing, it's all deterministic, so to speak. Yes, the underlying rules might be deterministic, but you can't know what those rules are going to have the thing do, except by essentially running those rules or effectively just watching what it does, which will be the equivalent of just running those rules. So I think that, in a sense, the idea of free will is a lot about this phenomenon of computational irreducibility, that one is not free if it is readily possible for someone from the outside to predict what one will do. If the only way to know what one will do is essentially to run oneself or to run something equivalent to oneself, then in some sense, that is something where one is free of sort of determinism, in the sense one is freed from sort of the ability that one's freed from sort of the obvious determinism, where there will be an ability to sort of jump ahead and see what happens. In a sense, I think free will can emerge from a deterministic system with this gap of computational irreducibility between the underlying determinism and the actual behavior of the system. Now, you can unpack a lot of things about these ideas about free will. For example, if I do something terrible, am I responsible for what I did? Or do I just say, no, I was just following the rules by which I was made, and so I'm not responsible for what I did? Well, it's not really a good argument, because it is you intrinsically that follow those rules are you, and it is those rules that cause you to do what you did. So in some sense, you are quite responsible. If instead what you say is, well, my rules are very simple, and all I'm doing is being buffeted by the outside world. Something happened to me, and so that caused me to do this, and it wasn't up to me. You could say in that case, it wasn't up to me. It was something outside me that I just sort of immediately translated to doing the thing that I did. As opposed to the case of computational irreducibility in me, where something might have happened from the outside, but there's this irreducible computation that's happening purely in me that caused me to do what I did. And so that second case, where even though it's deterministic underneath, the computation sort of all happened within me, gives me, in some sense, responsibility for what I did. There's intrinsic to me something that's going on that's causing that to happen. So it's like if you have a computer and some future AI, and it does something terrible, and you can say, well, it did it as a result of the intrinsic things going on in that AI. You might say that's a bad AI, let's switch off that AI if one's allowed to do that, and so on, because it's a bad AI, rather than the other AI, which just got, a programmer typed something in that immediately caused it to do this bad thing. You say, well, that's not the fault of that AI. The AI isn't responsible. It's merely from the outside. The AI itself is blameless. It's not something intrinsic to the AI. Now, you might ask, in this model with the ruliad and sort of our perception of the universe, how does the notion of sort of choice work in that case? And I have to admit, I have not thought this through completely. So it's that's a case where one of the things that's a bit confusing about that is it is a key part of kind of the experience we have of the universe that we believe that we have a definite thread of experience. It is, in other words, we could, that is part of the defining characteristic of how we parse the universe is this belief that we have a single thread of experience, the belief that we are persistent in time, the belief it's the same us as a few seconds ago. That, in some sense, is an arbitrary choice. In some sense, that is merely our way of describing the world. And I think that one can kind of see how that merely our way of describing the world thing turns into something about kind of the way that we make choices. But I have to say, that's on my to-do list to untangle that piece of philosophy, and I don't think I can do that in real time. So a bit of a philosophical cliffhanger there. I can't tell you exactly how that works. So let's see, a comment here from Craig. Every observer observes the same dimensionless constants, like the fine structure constant. We don't have any choice about that observation, or is 1 over 137 that lies on a sort of observable manifold of the ruliad. Okay. I think this just played into something good here. So first point to make is Craig is mentioning this thing, the fine structure constant, usually called alpha. Its value is about 1 over 137. It's just a number. It doesn't have units. It's not in meters or seconds or anything like that. What is it? It is the thing that in theory of quantum electrodynamics, it is the thing that tells you essentially the strength of electromagnetic forces. It is when you have two electrons and they have a force between them. It's the thing, it's the sort of dimensionless thing that determines the size of that force. So it is, we could imagine a world in which that number is different. We can imagine a world in which electrons have a different force of attraction between them. And for example, where the ratio of the electric force to the gravitational force of electrons is different. That also depends on the electron charge to mass ratio. But the intrinsic strength of the force due to gravity and due to electromagnetism could be different. Okay, so the question is there a different universe, could we be different kinds of observers where we wouldn't find the result that this dimensionless force on the electron is 1 over 137? The answer is absolutely yes. And you don't even need all this elaborate new kind of fundamental theory of physics. That even happens in traditional particle physics. So let me try to explain this. So the buzzwords for this are, think of the renormalization group and think of running coupling constants. And here's how it goes. So let's see. Basically, the point is when you probe an electron with a different energy, you will find a different effective value for its electromagnetic coupling strength or its fine structure constant. Roughly, the question of sort of what the force between these electrons is affected by just how hard do you kick it. If you're kicking it really hard, you'll see a different effective force and a different coupling constant, a different value of alpha, the thing that sort of couples these electrons together, than you would if you kicked it with a different energy. Okay, why does it work that way? In sort of traditional quantum field theory, the reason it works that way, okay, so in the case of the, let me mention something. It's an important effect in particle physics. It's called asymptotic freedom, and it relates to quarks. So inside a proton, there are roughly 3 quarks. There are a bunch of extra quark-anti-quark pairs and things, but they're roughly 3 basic quarks that are the inner structure of a proton. But you might notice that nobody has said, well, we'll give you a bottle of quarks. It's just there are protons, there are neutrons and so on, but there are no individual quarks. That's because quarks seem to be permanently confined inside protons. They have forces between them that are associated with gluons that basically that pull these quarks together. With electrons, with electromagnetic forces, if you pull them apart, if the further you pull them apart, the less force there'll be. Same with gravity. The further you pull it apart, the less force. It goes down like a 1 over the distance squared and so on. With quarks, the so-called color force or the force associated with the gluons does not go down as you pull them apart. Instead, it actually gets stronger as you pull the things further apart. It's like having a string or a spring between these quarks. The further you pull them apart, the more force there is to pull them back together again. So turns out that a big thing was discovered in 1973 is that if you kick these quarks really hard, then at least for a little while, they'll behave like there isn't much force on them. It'll be kind of that whole spring thing doesn't sort of cut in for a little while. And so that meant that it was possible to do experiments where you could kick the quark really hard and you could kind of see the effect of the quark wobbling around independent of the fact that it was sort of locked in place by this gluon forces and so on. And so that was sort of a big discovery, because when it's sort of locked in place, it's very hard to do the mathematics to work out how things work. But if you can get it, you can kick it hard enough that it behaves as if it is only very weakly coupled, it can just move more or less freely, then it's kind of easy to work out the mathematics. And that was a very important thing in the 1970s. In fact, I was quite involved in figuring out some of how that works. But in any case, that is an example of where, depending on how hard you kick the quark, and by kicking, I mean you have a particle accelerator, and you have high energy electrons, and you're colliding them into protons and so on. And it's a question of how much energy there is in that electron that's colliding with the proton. That's what I mean by kicking it harder, and so on. Depending on that energy, more accurately, the transverse momentum, but that you can roughly consider it the energy. You will effectively see a different effective value for the strong coupling constant, usually called alpha sub s. Same thing happens with electromagnetism, although the effect is much weaker. Turns out in electromagnetism, actually, that the harder you kind of kick the electron, the stronger the effective forces will seem to be. In the case of QCD, of theory of quarks and gluons, the harder you kick it, the weaker the force will seem to be. In the case of electrons and electromagnetic forces, the harder you kick, the stronger the force will seem to be. Roughly, the reason for that is that around every charge, electron might be a very tiny thing. We don't know how big it is. It's always been thought to be of zero size. In our model of physics, it's not of zero size. It has a size. It's very small compared to what we can see experimentally, but it does have a non-zero size. But that electron has a sort of whole coat of electron-positron pairs and all kinds of complicated quantum field fluctuations and so on that exists for any electron. Any electron is producing all these effects of little quantum vacuum fluctuations and all kinds of things like this. Well, the harder you kick it, the deeper you see into that coat of other things. And that coat of other things tends to shield the charge of the electron. So the effective almost electric charge of the electron is effectively smaller. I'm eliding a whole bunch of technical detail here, but effectively the thing you see, sort of the outer coating of the electron, at the scales we look at it, it seems like the electron has this electromagnetic sort of effect that corresponds to 1/137. If you kick the electron really hard, it's not going to be 1/137 anymore. It's going to be 1/100, or it's going to end up being 0.1, or eventually it's going to get actually really big. If you can drive down with higher energies, if you can see even closer to that very, very tiny inner electron inside its kind of coat of other quantum effects, you'll see a larger coupling. And actually what people think happens is, right now there are forces like the forces that hold nuclei together, the QCD forces, the weak nuclear force, the electromagnetism. These are all different kinds of forces with very different strengths. This idea of running coupling constant means if you kick things very hard, if you kick them with an energy corresponding to, let's see, it was 1,000,000 times the mass of a proton, basically. If you convert 1,000,000 masses of proton immediately into energy, you will get to an energy at which, if you kick particles at that energy in some sense, all of these coupling constants, like the fine structure constant alpha, they'll all appear to be the same value. And that's a thing, it's kind of that's sort of a thing that reveals the fact that fundamentally these underlying forces have something in common, they sort of unify. But it also says that it depends on how you look at it. The fine structure constant, even in traditional physics, is its value of 1/137 is a consequence of looking at it at very low energies. If we looked at it at higher energies, if we were, and in the translation that comes from the uncertainty principle and the way quantum mechanics works, if we were essentially very much smaller critters, we would be effectively operating at higher energies, and we would be sort of seeing something where we no longer see 1/137. You wouldn't say, oh, the fine structure constant is 1/137. You would say the electromagnetic coupling constant, the fine structure constant, is actually 1/100. If we were, oh, I don't know how big we'd have to be. Let me think about that for a second. Gosh, can't do this in my head. I think if we were a trillionth of the size we are, we would conclude about, I'm sorry, I'm not able to do this. It involves some logarithms and other things which are far beyond what I can do in arithmetic in my head. I think on that kind of scale size, we would be seeing an effective fine structure constant of order 1, not of order 1/137. So that's a sense in which even in this very traditional physics, even before we go to completely other ways to parse the universe, we see a different value of the fine structure constant. RBS is commenting, what if the beautiful images of stars and galaxies is really a molecule in another universe, and time is very, very slow in that universe from our point of view? Yeah, I mean, look, the fact is, I don't know, if we talk science fiction movies, there's a lovely sequence in Men in Black, I think, that shows kind of the whole, you know, the galaxy rolling up into a marble, and then sort of the whole universe is actually put inside this little marble or something. And yes, there is a sense in which if we were critters that were the size of a galaxy, we would have a completely different experience of the universe. We would have different physical laws. For us, you know, the speed of light will be really important. You know, most of the time, well, except for our internet connectivity or something, we're starting sort of an interesting thing, isn't it? That if you look at sort of the experience of us up until a few decades ago, you know, where does it matter what the speed of light is? It doesn't really make, you know, we don't experience anything that cares about the speed of light. We're just, oh, it's fast. You know, speed of light, speed of sound, maybe they only differ by a factor of 10 or something. It's actually much bigger than that. Right? It's actually a factor of 1,000,000. So it might be that, you know, for a typical experience of the world, we might say, oh, I don't know, light seems to go fast. Maybe it's 10 times the speed of sound. Actually, it's 1,000,000 times the speed of sound. Where does that matter? In the past, with the technology that we had in the past, it really didn't matter much. There were, you know, indirectly, there were things about, you know, the operation of a microwave oven and how big the thing had to be and all that kind of stuff to get a certain frequency based on size of the water molecules and so on. You could deduce how big the speed of light had to be and why it matters to sort of consumer appliances and things, but it's an indirect kind of thing. Now, with the internet and the fact that we've got sort of signals going through, well, often fiber optic cables, where they go at about 2/3 the speed of light, typically. Through glass, light doesn't go quite as fast as it does in a vacuum, and fiber optic cables are basically glass. We're starting to have more experience of the speed of light, because it's kind of like, oh, we're pinging this website that's on the other side of the earth. You know, we have more direct experience of, oh, it took, you know, 1/10 of a second to ping that website on the other side of the earth. So we're starting, our sensory experience is starting to include things that affect the speed of light, that are affected by the speed of light. If we were intrinsically, if our brains were vastly extended and the size of planets or something like this, we would have known about the speed of light forever, because it would have been a critical thing in the way that we would operate in the world. And so, yes, it is certainly the case that one could, one's description of the world depends on the way that, on things like the size one's at. And for example, for us, it's a big deal that our brain is really slow compared to the speed of light. In other words, we look around us, I'm looking out of a window here and I can see maybe, I don't know, 50 meters away. And, but the time it takes light to come from 50 meters away to my eye is absolutely tiny compared to the time it takes the neurons in my brain to register that particular visual scene. So for me, the light has arrived instantaneously. I can describe everything that I'm seeing as happening at the same time, even though something I'm seeing, might be 10 centimeters away and something might be 50 meters away. It's still, those things seem like they are, the light coming from them seems like it's reaching me simultaneously, so to speak, because my brain is processing things really slowly compared to the speed of light. If I was sort of very different in size, that would be, and I was routinely looking to the other side of the earth, for example, it would be something, and it mattered that things were coming back from the other side of the earth, as it does for the internet now. I would be experiencing things that are affected by the speed of light. And I might have a different model for how the world works than the one that we have. So let's see. Parmenides is commenting, if I always thought that if we are like bacteria living on a bit of sand on the bottom of an alien's shoe while they ride an elevator, what happens when the elevator stops? Yeah, I mean, we are but riding in, for example, let's imagine that there was some big sort of tear in space-time. So, a black hole has an event horizon. We don't actually know all of the weird pathological things that can happen in space-time. So, for example, in our theories of physics, there are possibilities of things I've called space tunnels, which are things where essentially you can have a part of the universe that has a different number of dimensions of space, and you can kind of, you can use that to, it sort of connects different parts of the universe in a different way. There are all kinds of weird pathological things that could happen. And yes, it could be the case that there, somewhere in the universe, some sort of tear in space-time happened. It'll travel towards us at the speed of light. We're not going to know it's coming until it hits us. And so in that sense, it could be the case that we're just riding on some feature of the universe, and there's a much bigger feature of the universe that we just are completely unaware of up to now. For example, and by the way, I mean, one of the things to realize is, for example, in the center of a black hole, where time stops. In our model of physics, time is the result of this progressive rewriting of this network of atoms of space. It's like this computational rule that keeps on getting run whenever it can be run, and time passes because that rule is happening. And so we're experiencing things because our brains are being run according to that rule. So in other words, we might say a trillion runnings of that rule, that corresponds to a second of experienced time. And if those rules weren't running, our time wouldn't be running. We wouldn't experience anything. So for example, at the center of a black hole, in our model of physics, those rewrites just stop. There aren't any more that can be done. There's nothing more, time stops. And the question is, what do we experience when time stops? And the answer is we experience absolutely nothing, because there is no, our experience is the result of our brains doing things and progressing, which we describe as progressing in time. But if we look at it microscopically, it's just the running of these rules. And so if those rules stop running, there is no experience. So in other words, one can think of, you fall to the center of a black hole and it's like, oh my gosh, everything's over. Well, yes, everything is over, but you don't experience, you don't have this horrible feeling, oh my gosh, everything is over. There's nothing to feel because experience has stopped. And And so, something like that could conceivably happen in a universe. I think it seems super unlikely, but that's a sense in which we are but riding on the back of this kind of this whole thing that is our universe, with all kinds of effects that we have little control over. I mean, for example, one thing that could happen, a star near us could turn into a supernova, could explode. I think that there is an imminent danger of that. I don't think there are any stars near us that are big enough to, except for stars that we've studied quite well. By the time they're big enough that they have the potential in 1 billion years or something to turn into a supernova, we can see them now, and we know we can check that they're not turning into supernovas. So I don't think that's a high risk kind of proposition for right now. Brian is asking, is there a maximum to how fast we can think? Yes. I mean, at the level of the universe, doing its computation to work out the next step of the universe, then absolutely the best we can ever do is we are essentially existing in that system that is progressing, that is sort of determining what the next state of the universe is. Our brains are merely part of that. So there's no sense in which we could outthink the speed of the universe. Well, I mentioned this phenomenon of computational irreducibility. We could say the universe is going through and it's doing all these complicated computations, and we can do clever mathematics and jump ahead. But if we're just emulating the actual steps, which, by the way, we can't usually do, but if we were just looking at the steps the universe goes through, we can say, well, could we speed up those steps? And the answer is, well, the universe is doing what the universe is doing, and we are part of that universe. So we are taking the same steps the universe takes. So in some sense, there is a sense in which there's no way we can outrun, we are part of the universe, so we can't outrun it. And our way of measuring time, it's all a bit circular, because our way of measuring time is based on our experience of time, things happening, and the thing that determines, I don't know, the transition in the cesium atom or something, which is the standard of time these days, is determined by its some number of update steps in the evolution of the universe. And so that's our measure of time is based on the number of update steps. And our ability to think, so to speak, to compute in the universe is also just based on these update steps. So we can't kind of outrun that. Now you can say, what is the processing speed of the universe? What is that maximum speed? And we don't know yet, because there's an important parameter in our models of physics, which essentially determines the elementary time or the elementary length. It determines when sort of two successive rewrites happen in this network, what is the amount of time that we assign between those two updates. So in the end, gazillions of those updates will do the things that constitute what we identify as 1 second of time elapsing. But the question is, how many of those are there that correspond to something that we identify, like this transition in the cesium atom or whatever it is, that we identify as being the elapsing of 1 second of time? And we don't know the answer to that. We don't know what that parameter is. I'd really like to know. Hopefully, in the next few years, it will be possible to do experiments to determine that. We don't know that. So we kind of think maybe it's a trillionth. I'm still not doing very well counting on my fingers. Another trillionth of a second is the elementary time. And if you know the elementary time, you can estimate, well, there's some other things you have to estimate. You need the intrinsic parameters of the model are the speed of light, a thing we call the maximum entanglement speed, and a thing we can call the maximum rulial speed. These are sort of three parameters that determine the structure of this model. We know the speed of light, we don't know the other two. But if you make sort of very rough estimates, the maximum processing speed of the universe is, you have to measure it in terms of the speed of doing computations. So the speed of taking a program and processing that program. And so, for example, let's imagine we have a Wolfram language program. We can say how many tokens are there in that piece of Wolfram language code, and we process those tokens at a certain rate per second. And so I had one estimate that it's a 10 to the 450, in other words, a 1 with 450 zeros after it, is Wolfram language tokens per second, is my rough estimate of the processing speed of the universe. So that would be the maximum speed at which any computational process can happen in the universe. Now, building an actual machine that would be where we would be able to understand the output and so on, far away, far, far away from that. I mean, just to talk about sort of computation, and one of the things I've been thinking about recently is computation at a molecular scale. Computations we do right now are based on packets of 100,000 electrons in a silicon crystal and so on. That's how computers work right now. But the question is, if you were to be able to do a computation at the level of individual molecules, what could you achieve there? And what could you do? What kind of observations can you make when, let's say, you've got these configuration of molecules? So I kind of suspect that in biology, there are many situations in which you get some elaborate configuration of molecules, which means something to the biological system. But the chemist right now just says, oh, there's a certain concentration of that chemical. They're not taking account of the sort of subchemistry of seeing the actual positions of all these molecules. And when we have something like a crystal, we know all the molecules, all the atoms are nicely lined up. But I was just looking actually at cell membranes, where you have all of these proteins that are sort of sticking through cell membranes in what seems like kind of a random arrangement. And there's sort of a question of how those things are, what is there in fact information? Is there some representation? Is there at a molecular scale? Is the answer written in the configuration of molecules on the surface of a cell, for example? We don't know that yet. Anyway, this is something I've been thinking about. But this is in terms of sort of different experiences of the world. That's a very different level of experience. If your experience is something, if your experience is down at the level of sort of proteins on a cell surface in a biological cell at a very microscopic scale, you can end up with a very different kind of view of physics and so on than we have at the scale that we're at. All right. Well, we should probably wrap up here. I think I'm late for something else. But that was fun. You guys are getting me to do a certain amount of somewhat real-time philosophy. And this is these are kind of, we're diving into pretty deep questions about sort of, well, I would say even life, the universe, and everything in some sense. I hope I've been able to explain this in a way that people can follow. I think the thing that is sort of exciting at a meta level about these kind of philosophical questions is a lot of these questions have been solidly around for 2,000 years or more, of people thinking about, how is motion possible? What is the world made of? In what sense is there some, is experience real? These kinds of things. And, it's rather exciting to have been able to, from the point of view of science, which is a very specific kind of way of thinking about the world, we're able to sort of build this tower that reaches back into these questions that really were questions of sort of fundamental philosophy back a couple of thousand years ago. And I'm at least having fun sort of untangling these kinds of things. And I'm kind of like, if only Democritus back in, I don't know what, 400 something BC, if only he'd had a computer and he'd understood this idea of computation, what different conclusions would have been drawn in the very early days of sort of pre-science as we know it today. And it's certainly a historical amusement in a sense that there were sort of, at least one example of sort of a clockwork type mechanical computing device that existed in antiquity. It's not known how common those were, but I kind of just imagine of, people didn't yet get the idea of the sort of abstract notion of computation. And had they got it, sort of the history of science would have been very different. And that would have been a a sort of a different way of seeing the universe, and we'd be having a quite different discussion about sort of these are the laws of physics as we know them, and there might be other ones that were known to the aliens, but those aliens were the branch not taken of the development of human science. All right, I think should wrap up here, and let's see, we'll be, I think next Friday, I may not be able to do this at least at the same time. So if you can see on our website, I think, or on our Twitter when we're doing these, but I'll do them. I have another one next Wednesday, which will be about history of science and technology, and next Friday at some time, I think, a continuation of this science and technology Q&A for kids and others. All right, thanks for joining.